We are all familiar with the arithmetic functions: addition, subtraction, multiplication, and division. If I give you two decimal numbers, 9 and 3, and I ask you to perform addition operation on it, you'll give me your answer, 12. How did I get that answer? Well, 9 plus 3 gives you 12, but you take 2 down here and you pass a carry to the next stage, and that carry would go as a 1, but in reality the value of that carry is 10, because whenever you pass a carry to the next stage, the value of that is going to be the value of your base. So in this case we have a base of 10. That means the value of this carry is going to be 10. So then I bring this carry down because I don't have any digits over here, which I can assume is 0, so I get a 12. So that's my answer for this. We need to understand the binary arithmetic because all the microprocessors and controllers have binary arithmetic operations and functionality built into it. So let's start with the addition. To perform the addition, you have to bit by bit addition starting from the least significant bit, and you need to pass the carry to the next position. Let's say I take the equivalent of these two decimal digits in binary. I will have 9. 9 is going to be 1, 0, 0, 1, and 3 is going to be 1, 1. And I ask you to add them up. Now my least significant bit is right here on the very rightmost side. So this is my least significant bit. So I'll start from here. So 1 plus 1 gives me a 2, but there is no 2 in binary number system. Whenever we get to 2, we are actually talking about 1, 0. That is my 2 in base 2, which is equal to 2 in base 10. So 1, 0 in base 2 is equal to number 2 in base 10. So over here I have 1 plus 1 results me a 0 down here, and I have a carry of 1 that goes to the next stage. Now keep in mind that the actual value of this carry is still 2 because that is my number system. We add this carry of 1 into this 1 and I again get a 2 or a binary 10. So I write my 0 over here and I take the carry to the next stage. I add 1 plus 0 gives me a 1, and this one here has nothing to add, so I just bring it down. Now if you would convert this back into your decimal number system, you get 12, because this here, the value of this bit is 8, the value of this bit is 4, so 8 times 1 is 8, 4 times 1 is 4, 8 plus 4 plus 0 gives me back 12. Now let's talk about subtraction. Subtraction works about the same way as it would work in decimal number system. So if I take the example of these two numbers again, so 9 minus 3, that gives me 9 minus 3 is going to be 6. In this particular case, I do not have to borrow from the next position, so it was pretty straightforward. The subtraction in binary, you have to do bit by bit subtraction starting from the least significant bit, and you will borrow a carry from the higher position bit if it is needed. So let's go with these two numbers again. So I start with 1, 0, 0, 1 and 1, 1, and now I am going to subtract it. So 1 minus 1, that is simple, gives me a 0. Now I have to subtract a 1 from 0, which is not possible. So I go to the next higher position to get a borrow, but that's a 0. So then I go to the next position to get a borrow. So I will borrow this one over here. Now when I'll bring it down over here, what is the value of that borrow? The value is going to be a 2. Out of this 2, I will borrow 1 again over here. Value of this borrow is going to be 2 again. So 2 minus 1 gives me a 1, and I am left here with only 1 because I borrowed 1 to this lower position. So I am left with 1 over here, and down here I have only a 0 because this one was borrowed down to the lower position. Now this number over here is equal to 6. Let's talk a little bit about multiplication. Now, multiplication works in the same way as in decimal system. So you start from your LSB and do bit by bit, and you add the individual results to find the net result. So if I start with these two numbers again, so 1001 multiplied by 1, so 1 times 1 gives me 1, 1 times 0 gives me 0, 1 times 0 gives me 0, 1 times 1 gives me a 1. And then uh, on the next line I move left, just like we would do in a decimal multiplication. So 1 times 1 gives me a 1, 0, 0, 1. And then I simply add these two, and this would give me 1, 1, 0, 1, 1. Now, this number here, that should equal to 27, because I know 9 times 3 is 27. Let's convert this number into decimal. So the number that I'm converting is 1 times 2 raised to power. So 0, 1, 2, 3, 4. So 2 raised to power 4 plus 1 times 2 raised to power 3 plus 0 times 2 raised to power 2 plus 1 times 2 raised to power 1 plus 1 times 2 raised to power 0. So this gives me 16 plus 8 plus 0 plus 2 plus 1. So 16 plus 8 is 24, plus 2 is 26, plus 1 is 27. So far we have discussed the natural binary numbers. A natural binary number is a direct conversion of a decimal digit into a binary number. We looked at 123, which was converted into 011, 1011 base 2 using successive division. Binary codes, on the other hand, are assigned binary numbers to various alphanumeric characters. While there are many binary codes available, two of the most common ones are ASCII code and BCD. ASCII code stands for American Standard Code for Information Interchange. It is a 7-bit code for the alphanumeric characters. 7-bit means that you can encode 2 raised to power 7, so a total of 128 possible combinations. That means you can represent 128 alphanumeric characters. While full tables of the ASCII code are available online, I have plugged few values over here. So let's take a look. 7-bit binary number with all zeros represents a null character in ASCII. A null is nothing. It is not a zero, it is not a space, it simply means nothing. A space has a binary code of 01000000, and the digit 0 has a binary code of 0110000. Now we can convert these binary numbers into the equivalent decimals so that we can read them easily. A null is a decimal 0, a space is a decimal 32, a 0 digit is decimal 48. See how it is different from our natural binary, because natural binary for 0 is all zeros, whereas in ASCII we are assigning this 0 a 7-bit code representing decimal 48. A capital letter is assigned a decimal 65, which in binary is 1000001, and a lowercase is assigned decimal 97. You can pull up a full ASCII table online. In this particular example, I have 4 columns. If you look at the column 1, it represents codes from decimal 0 to decimal 31, and the binary for each of those is given right next to it. The interesting values over here are null, which is represented by a decimal 0, a carriage return, which is represented by 13. Carriage return is the code that is generated when you press the enter key, and escape, which is decimal 27. In the second column, we go from decimal 32 all the way to decimal 63, and again the binary equivalents for each of these decimal values are given right next to it. The interesting values over here are decimal digits from 0 to 9. 0 is 48 with its equivalent binary value, 9 is 57 with its equivalent binary value. In the third column, we have capital letters from A to Z. A starts at decimal 65 while the Z is decimal 90. In the last column, we have lowercase characters with A decimal 97 and the Z having a decimal value of 122. You may ask how 123 would be represented in ASCII code. Since each one of these digits is represented by a 7-bit code, we need 21 bits to represent 123 in ASCII. From the table, we know that ASCII code for 1 is decimal 49 or 0110001. So I'm going to go ahead and write that code over here, 0110001. For 2, the ASCII code would be decimal 50 and binary would be 0110010. And for 3, it will be 0110011, a total of 21 bits required. We can add one extra bit to the left on each of these so that each one of this is a byte. So essentially, we will be representing the ASCII code for 123 with 3 bytes. The second of the binary codes that we'll talk today is BCD. It stands for binary coded decimal. BCD is a 4-bit code and it represents digits from 0 to 9, hence binary coded decimal, 0 to 9 digits. Now we use 4 bits because if you use only 3 bits, 2 raised to power 3 gives me a combination of 8, whereas 2 raised to power 4 gives me a combination of 16, and since I have 10 digits, this is my viable option. I have reproduced the BCD table over here. 0 is represented with 0000, 1 is represented with 001, and 9 is represented with 1001. Note, all of these values, natural binary values for each of these digits. So how does BCD differ? Well, if I write BCD for 123, so 123 in 10 in BCD, it is going to be, we know that it is going to be 4-digit code, so 4-bit code, so I will write it for 1, I will write it 0001. For 2, it is going to be 0010, and for 3, it is going to be 0011. So this is my BCD for 123.